I'm back working on this Elektronika D3 Nixie tube calculator. As you can see, it's not working properly. So although all the digits now work, I had a problem with one of the digits not coming on at all, and that was a failed capacitor on the Nixie tube driver board. So I've replaced that capacitor, so now all the digits at least come on. But as you can see, it's not working properly. All the decimal points are on, at least all the decimal points on the Nixie tubes that have a decimal point. They're all on, and obviously they shouldn't be. Now it does respond to key presses to a certain extent, in that depending on which keys you press, it may do something and then you can clear it. But clearly it's not doing what it should do, and it doesn't carry out any functions properly whatsoever. Doesn't matter which keys or which buttons you have selected, it just doesn't work the way they should do. So the next issue I had was how to go about trying to fix this, and there are many ways you could go about this. It depends on experience, the equipment you have, and the information you have, the documentation. But this was always going to be a challenge because it's Russian built, and because of when it was built, the information that's available was always going to be fairly difficult to follow. I was very lucky with this. I had two people watching the videos. One sent me a link to a data sheet or data book that has data for most of the ICs in this. Again, not easy to follow, but that is extremely useful. And then somebody else was kind enough to send me a set of schematics for this, or at least kind of for this. We'll come back to that in a few minutes. But even so, the next step was how to go about actually fault finding on this. I'm going to turn it off. I don't want to leave it on too long because I don't really know what the fault is. I don't want to do any more damage than we absolutely need to. Now, because of the way this is constructed, we've got this rack at the back and all the cards sit well down into it, so we can't really access the back of the ICs or the top of the ICs with them fitted into this rack. Unfortunately, the boards are conformally coated, so even when you get access to them, it's quite difficult actually making contact with scope probes and the like. You can do it, but it's fairly difficult, and you need the boards fairly well secured in order to do that. So really the next step was to find some way to access the boards while still running the machine. So I took a bit of a break from this so that I could put together some risers. So I designed a riser board, and this is obviously to fit into this rack. I made it single board but a double height one, so if I want to, I can make risers either the short height or the tall height, depending on where I want to put the riser, or if I want to put a board low down and a board high up. All I do is cut off the board, put the connectors on of the correct height. I have a riser of the height that I require. But I did have an issue in making these, and that is the pitch of these connectors. On this machine, the connector pitch is 3.25 millimeters, which is a bit of an unusual pitch. The nearest standard one I could get, at a sensible price anyway, was 3.18 millimeters. And although it's quite a small difference, and it will be fine for anything 10, 11, 12 pins, anything beyond that, and there are 22 pins on each of these connectors, and over the span of 22 pins, the cumulative error would be such that by the time you get to the 15th or 16th pin, the connectors would not be aligning properly. Even if you kind of jiggle them about a bit to center them, the extreme, the ones at the end, would be running off the fingers on the edge connector. So what I ended up doing was getting some connectors at 3.18 millimeters, and I used a slitting saw to cut them in half so that I could effectively increase the span of the connector. So the nominal connector span is now 3.25 millimeters. Obviously they're not all correctly spaced, but the error as we go through is sufficiently small and the way I've arranged this is the two outer ones, or two outer halves, are arranged so that when you put a board into it, it properly centers the board, and the errors are kind of nulled out at the center point, and then the cumulative error starts again, but it's only half what it would have been. So it's now easily, all the connectors now easily sitting on the proper part of the edge connector when we put a board in there. The risers themselves, obviously I made these the correct pitch, because I could make these whatever I wanted to, so they are the correct pitch and spacing for our actual machine. It was just the edge connector that was an issue. So when I fit an actual board that has the correct spacing, then, although you probably can't see it, all the pins now properly line up. So that's a working riser. I can now take the boards out, put them into the riser, and that will give me access, and I can start probing around. Now, of course, that comes to the next question as to where to start. And I was looking through these schematics. As I said, somebody was kind enough to send me a set of schematics. They look quite clear here, but they're not as clear as they first seem. This is after a lot of enhancement, and somebody suggested OCRing this because, as I said, that all the text was in Russian, and I don't speak Russian, and it would be quite useful to know what all this text says. Would make the schematics far more readable. I'm not particularly concerned about the data book text. The data sheets, I'll give you an example of what's in there, look like this, and although I can't read the text, I know what it says by the values, but really it's the schematic for the inner workings of the IC I'm interested in, and more specifically the pinout. And if you're familiar with Russian terminology on these, you'll know what this means. So you'll have something like this, and it will indicate whether it's an OR, AND gate, that sort of thing. So you've got an OR gate here, which is what this symbol means. You've got AND you may have a mixture depending on the particular device that you're looking at. So I don't really need to get the text for this, and I have printed off the relevant sheets for the ICs I've looked at so far, and just made notes as to what these actually are. And so this is extremely useful. This was from the data book, although you can find the data sheets for some of these devices. Where it gets difficult is that because of the numbering system and the way it changed over time for Russian machines, the number that's printed on or stamped onto the device is not the same as the number that's in the datasheet. It's got some similarities, but it's a completely different number if you just look at the number in terms of the way it's written down. So that's a bit of a pain, because it means it takes a bit of detective work trying to figure out which particular device in the data book a device on the board actually is. So the way I go about this is I look at the schematic, see how it's configured, what the pins are connected to, and then if we need to, we can put a scope on it now and just confirm that I've made the right assumption, but I will need to check various or multiple devices, because we know at least one device in this machine is not working. So as I said, I'm not that concerned about the text in the datasheet. This is all information that I need from the datasheet. But it's the text on the schematic that would be useful. But as I said, you can't really successfully or easily OCR this. You can OCR images. In fact, I did one a few days ago. This is from another project I'm working on. We'll be posting some videos about this. This was obviously, as you can see, Chinese. You won't be able to read all this, but all the text was in Chinese, and it's a JPEG image. But what I did was to effectively convert it to English so I could read it. And the way I went about doing this is I created a version of this schematic image. I cleared out all the text so it was just blank, and then I cut and pasted the blocks of text into a translate program that could translate images, and then I pasted the translation back into the blanks that I'd created, and I end up with a readable schematic. It's very time consuming, so it's not something I want to do if I don't need to, but just trying to OCR this in its entirety in one pass would not be very useful. If you speak Russian and you'd be willing to just comment, what I could do is show all these on a video, and I just need this text in the bottom right is a good starting point to indicate what each of the boards is supposed to do. So that's where I got to as far as the initial assessment was concerned, and then it was, well, how shall I go about fault finding on this? It's typical, whether it's Russian or US or UK, doesn't really matter. I tend to follow the same process. So I decided to start on the first board, board 1, which is this board, and I'll explain why. I'll just pop the board out. I've popped the board out. Now, I said earlier that the schematics kind of match the machine, and this is an example of what I'm talking about. It's also why I never make assumptions as to information that I am given. The information, the schematics, will be incredibly useful for fault finding on this machine, as long as I understand that it's my responsibility to figure out what I'm looking at. And to give you an idea, if I put this board down here and we look at the schematic, this is the schematic for board 1. So if you want to try and figure out what I'm getting at here, if you pause the video and then restart it once you've seen the thing that stood out for me. Okay, so if you haven't paused, we'll carry on. If you have paused and you've figured it out, then it should hopefully become clear why I decided to start with this particular board. If we count the ICs, and it's not drawn in such a way that the inner workings of a particular IC have been split into 2 blocks. The number of ICs on here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 20 ICs, 2 rows of 10. But if you look at the board, there's only 18 ICs on it. Every other board has got 20, at least every other short board has got 20 ICs, 2 rows of 10, which is what is shown in the rest of the schematics. But this board doesn't match this. Having said that, if we look at the schematic, then if you forget it's Russian, forget anything else, just look at the logic in here, you can see that this could be simplified quite a bit, and I've got a feeling that's what may have gone on here. Somebody may have kind of rationalized and simplified this schematic, and this might be a more recent version of this board. I don't know yet, I haven't looked into it in any real detail, but I need to try and figure out how to make sense of what we're looking at here. So I make a very brief sketch of the board. I give a designation to each of the ICs. A lot of the ICs are used in more than one place, of course, and I make a note of the number, but I translate the number, I identify the IC as it appears in the data book. So for example, the K172 TP1 is this device, so I now know what the pinout for the device should be, and the way I go about identifying this within the datasheet, bearing in mind that the number's different, is I look at the schematic. So if we look at the actual schematic for this particular board, one thing to bear in mind, of course, is we know at least one of these ICs on each row is missing. We don't know which one. It could be 2 on one row, of course, but if we look at the end 2 ICs on this, you'll notice that the pinouts are identical in the way that they're used, and as you can see, they also happen to have the same part number. So looking at the data book, I can then figure out which particular IC it is, and in the layout I can then start to figure out what it's supposed to be doing. So it's kind of almost a catch-22 when you first start, is which ICs are these. The other problem with this is when the designers of the ICs design the ICs, they used common pins for like outputs, so 6 and 10 it seems to be an output for all different types. So it's really a case of trying to figure out what's going on. And what I'll do as I go through this is I'll confirm the operation of a particular device to make sure that it is what I suspect it is. So in this case, this particular device I suspect is 2 4-input OR gates, or NOR gates, it depends on the sense of the outputs. And you'll notice that it even tells you which one is the output and which one's the not output. So these, unlike standard TTL, which tend to have a single output for each gate, these have complementary outputs. And again, that can be useful for identifying what's going on. So if we look at the designations for the data coming out and how they've been written, you might find that some are in a positive sense and some negative. So it's really going through and trying to figure out what we're looking at, coming back, checking it, and then we should be able to figure out what's supposed to be on the particular board. It should be easier for the other boards because they have the same number of ICs. Having said that, it doesn't necessarily mean they are the same ICs that are identified in the schematics. That's something we'll have to check as we go through. So now I have an idea as to what I think is in the particular layout. In this particular one, I believe that these 2 ICs are the ones that have been removed. But we'll come back to that as we go through the fault finding. What I can do now, of course, is fit the board to the riser. I can then fit the riser into the machine, and we'll start by making sure that the machine will still power up and do the same thing it did. In other words, we'll make sure the riser is properly contacting all the pins and doing what it's supposed to. I've got the board fitted to the riser. As you can see, it's a nice firm fit in here, so it's not going to flap about everywhere, and it should allow me to probe the board. But let's just make sure that this still works. So we should see exactly the same thing we had before. All the digits should come on and all the decimal points. So I don't know how well you can see that. And as before, if I press any keys, certain keys should cause it to do certain things. So as you can see, it's doing exactly the same thing as it was. So I can be fairly confident that the riser is doing its job. Okay, that's it for this video. The next thing we'll do in the next video is start working our way through the actual schematic. We'll try and confirm our suspicions about what each particular IC is. The easiest way would be to put a clamp onto the IC or a clip and use the logic analyzer, and then check that we're getting the correct logic behavior based on what we believe the IC to be. I might try that, but I don't think it will work because of the conformal coating on the IC. I don't think any of my clips will make good contact. I do have some knife edge clips that have very strong springs on, but even so I don't think they'll bite through the conformal coating, but I'll give that a go. If that works, it's going to make life a lot easier. What I may end up doing once I've confirmed the nature of the ICs and that they are the IC types I believe that they are, is we might just end up starting off by looking at the in-out connections. As I've said before, if we know what a particular board is supposed to do, then we can just look at its outputs and make sure that everything is behaving the way it should. So in other words, we can look at these pins, and if they are doing what they are supposed to, which I believe this is a not pin 3 output. In other words, I believe that if we press key 3, I think this should go low, and we can probe that, of course, on the actual riser without having to try and get through the conformal coating. If we find that most work and some don't, then that will be something we can fold back into this board. If everything's working and giving an output, then we can be fairly confident this entire board works and we don't need to mess with it. We can move on to the next board. So that's the approach I'm going to be taking. Hopefully this all made some sense. Apologies if it's a bit of a convoluted explanation. It's kind of a difficult thing to explain because there isn't a kind of sensible starting point for any of this. It's kind of all interactive and two-way, speculation, going back, confirmation, and then correction if I've made a mistake. But it's a lot of fun to do this, and it's a real good way to learn about electronics, and hopefully at some point we'll be able to locate the fault or faults and get this unit working. And as we go through, we'll use the information that we have, and hopefully it will make some sense as to how this particular machine actually works.